Section 1.3, linear equations in two variables. And what a linear equation means is that we'll be looking at straight lines, and in particular, techniques to graph straight lines, and how to find equations for them, given a couple points on the graph. So to start with, we'll introduce a definition called slope-intercept form. And the reason we call it this is that we will use the slope of a straight line and the y-intercept to give a nice equation. The general equation for a straight line is y is equal to mx plus b, where m is the slope of the line and b is the y-intercept. So the takeaway formula here should be this y is equal to mx plus b form. And we defined y-intercepts in the last section. This is the point on the Cartesian plane where we touch the y-axis. And we'll talk about slope a little bit more as we go on. So before we get into some complicated straight lines, let's look at a few simple special cases. So special cases. Our first is the equation y is equal to b. No matter what x value we put in, y will remain the same. It'll always be some value b that we plug in. And so this looks like a horizontal line at the point b on the y-axis. So maybe we'll graph one real quick here. Let's graph y is equal to 2. And to graph, we need a Cartesian plane. So I'll throw down a couple numbers here. And on the y value, we have 1, we have 2. And what this equation says is no matter what x value we pick, y will always be equal to 2. So there's our straight line. And you see as we vary x, y remains the same. We can do the same thing with x now. So the next special case is x equals a. And now, no matter what y is, x will always remain the same. So this is a vertical line at the point A on the x-axis. And again, maybe we'll graph a quick example. How about x is equal to 3? Draw our Cartesian plane. Here's -1, -2, 1, 2, 3. And a couple points on the y-axis, just for simplicity here. So no matter what y is, x will always be 3. So it's a vertical line, whereas we vary y, the x value never changes. It never leaves that 3 point. And now that we've talked about horizontal and vertical lines, we're going to start talking about slanted lines. So before we get into the details of how we find all these things, why don't we start by just graphing a straight line with the techniques we learned in section 1.2. And we'll graph y is equal to 2x plus 1. Now, one of the reasons we like linear equations is to get a good picture of it, we only need 2 points. And because we really only need 2 points, we normally use some small points. And we'll use 3 here. We'll use x is equal to -1, 0, and 1, just to get a little bit better view of what this will look like. So we think back to how we graphed in 1.2, and we remember we need to make this chart. X values are on one side, y values are on the other. And as said above, we'll use -1, 0, 1. And now we'll plug in these x values to our equation. So we get our y value is 2 times -1 plus 1, which is equal to -1. 2 times 0 plus 1, which is equal to 1. And 2 times 1 plus 1, which is equal to 3. Now that we have our couple points, we will plot them on a Cartesian plane. Oops, did that backwards there. So I have -2, -1, 0, 1, 2. And we'll go up to 3 on the y-axis. And we'll go down to -1. And maybe we'll throw on -2 here too. And now we'll graph this line. So when x is equal to -1, y is equal to -1. So there's our first red point. When x is 0, y is 1. And when x is 1, y is 3. And now we simply connect our dots here with a straight line. And we'll pretend this is a straight line. And we've done it. And we see that graphing these are quite simple. All we need to do is pick a couple small points, plug them in, and we can see what's going on here. One thing we should make a quick note of is this point 0, 1. Notice that our graph is equal to y is equal to 2x plus 1. So this 1 right here in the equation tells us what the y-intercept is right away. We should know that when x is 0, y is 1, just by looking at the equation. The next thing to note is that notice when we move 1 in the x direction, we move 2 in the y direction. And that's what this slope is. The 2 tells us that every time we move 1 to the right, we should be going up 2. Okay, so we'll move on here. So now we know how to take an equation and make the graph out of it. But what if we had the opposite? What if we have the graph and we want to find the equation? Well, with our point-slope form, this accounts to finding the slope and finding the y-intercept. And finding the y-intercept is easy enough. We just have to look at the graph. So finding the slope is the real trouble here. So let's talk about slope in a bit more detail here. So finding the slope. So what is the slope? The slope tells us how much y changes, or our y values change, as the x values move 1 to the right. We saw in the previous example, which we'll scroll up to, that the slope was 2 because as we moved from 0 to 1, the y values increased from 1 to 3, or increased by a value of 2. This means if we sort of look at how the values are changing on the graph, we should be able to find the slope right away. And how we do this is we use a change of value or a rate of change formula. And really all this means is that we'll be dividing. We divide change in y by change in x. Or, how some people say this is, it's the rise of the values divided by the run of the values. How far have we traveled up versus how long did it take us to get there? So let's draw a picture of what this means here. And let's say we have a nice straight line as such. And we're given 2 points on the graph. Let's say it's x1, y1, and x2, y2 is above here. Then what we're really trying to do is see how far has the x moved versus how far has the y moved. So maybe we'll do the y change in red here to really make it stand out. And now we can sort of see how we calculate this. If we're looking for this box here, the change in x and the change in y, just like before when we were using the distance formula, we should be subtracting the final position, the x2, from the beginning position, x1, and that tells us how far we've moved in x. And similarly, we can just take the y2, where we ended up, and subtract the y1, where we started, and see how far we've moved vertically. So, the slope m is equal to y2 minus y1, how much we've increased, divided by x2 minus x1, how long it took us to get there. And this gives us exactly what we're looking for. As the x changes, how much are we going up by y? So this is a very important formula, and we should make a quick note here. Note that if we look at the beginning values, we have y2 in front and we have x2 in front. And in the back, we have y1 and x1, and this is very important. We don't want to switch this up. y2 always comes first if x2 comes first, and y1 always comes last if x1 comes last. So the order matters. Make sure you're using the same point in the front and the same point in the beginning. Aside from that, calculating the slope is rather easy, and there's nothing really trickier to it. Next, we'll talk about finding the y-intercept. And we sort of have two things that might happen. If we have a very nice graph given to us, and if we can see the y-intercept, then we are done. We can just grab that point, plug it into the equation, and we're good. But if we're given an incomplete graph, or maybe we're just even given 2 points, and we want to make a graph or an equation between them, we have to do a little bit more work to get the right y-intercept. So now, let's assume this isn't the case. If not, then let, again, x1, y1 and x2, y2 be 2 points on a line. But now, let's also let x and y be variables. But we assume it is a random point on the line. So this x and y are allowed to vary, but we do want to make sure that it's still on this line we're trying to find. So now if we have 2 points, we know how to find the slope. So we'll just recall m is equal to y2 minus y1 over x2 minus x1. And now if we take any other point on the line, even if we don't know what it is, and we calculate this ratio, it should always give us the slope. Meaning that our weird random point, xy, should also give us this m. Or y minus y1 over x minus x1 is also equal to the slope m. Remember, m is a set value, y1 is a number, x1 is also a number, and this y and x are just variables we're trying to solve for. So now we have sort of a weird equation with some nice values plugged in. And let's see if we can get y by itself to make an equation. So what we should do is cross multiply. And we'll bring this x minus x1 here to the other side. So this becomes y minus y1 is equal to m times x minus x1. And we're almost done. The only thing we have to do here now is add y1 to both sides. And we have y is equal to m times x minus x1 plus y1. And we have a general equation for a given line that uses 2 points. It doesn't use us looking at the graph at all. It doesn't use us knowing what the equation is beforehand. Just if we have these 2 points, we can very quickly and easily get the equation. So remember that even though there's only an x1 and a y1 in this equation here, to find the slope m, we needed a second point, x2, y2. So we really do need these values. And we can rewrite this equation to say y is equal to mx plus y1 minus mx1. It's just a little bit of algebraic manipulation. And the reason why we might want to write it like this is because it looks like point slope. And if y is equal to mx plus b, then this weird plus y1 minus mx1 should be our b. And we have a nice way to easily find what the y-intercept is. So let's put this into practice. Let's do an example where we find the equation of the line. Passing through 2 given points. So we'll say it's passing through the point 1, negative 2, and 2, 1. So remember, the goal here is to find the slope and the y-intercept using what we have before. So this would be a good time to pause it, look through the previous notes, see if you can figure this out, and then we'll quickly do it at the end here. Okay. So if you've taken a shot at this, let's do it and make sure we're all right here. So remember, m is equal to y2 minus y1 over x2 minus x1. And how about we let this first point here be our x1, y1, and we'll let the second point be our x2, y2. And now all we have to do is plug it in. y2 is 1, So 1 minus negative 2 divided by 2 minus 1, x2 minus x1. And this is equal to 3 divided by 1, which is simply 3. So now we have the slope, and the last step is to find the y-intercept. Now we can either use the formula that we had above and just plug it in to see what b is going to be, or we can take it one step further back and use this y minus y1 divided by x minus x1 is equal to m formula, and see how it plays out. So we again cross multiply the denominator, and we'll end up with y minus negative 2 is equal to 3 times x minus 1. The 3 will distribute to both the terms on the inside. So this is y minus negative 2 is equal to 3x minus 3. And now we'll add negative 2 to both sides. Plus negative 2, plus negative 2. And we get y is equal to 3x minus 5. And there's the equation of our line. We can quickly check to make sure this works by plugging in x is equal to 1 and seeing if we get y is equal to negative 2 out. And plugging in x is equal to 2 and seeing that we get 1 out. So why don't we do that second one here? So if x is equal to 2, then y is equal to 3 times 2 minus 5, which is 6 minus 5, which is 1. 2, 1 is on the line. And now we know how to take care of every type of linear equation. If we're given a linear equation, we know how to graph it and see if our points are on the line. If we're given a graph, we know how to pick points and find the equation. Or if we're just given 2 points, we can make a line between them and find the equation using nothing more than those 2 points. So at this point, we've mastered straight lines, and we've seen they're quite easy. So now let's start using them in a little bit more interesting of a way. And we'll do that by defining parallel and perpendicular lines. So what is a parallel line and what is a perpendicular line? Well, why don't we show with drawings what it means to be parallel and perpendicular, and then we can see what this means algebraically. So let's start out with parallel. 2 lines are parallel if they run simultaneously next to each other, sort of like comrades in arms. They're sort of the same line, just shifted. I'm going to try that again. Just shifted sort of up or down, and then they can be right on top of each other. Or in other words, if we look at how the x and the y change, it needs to be happening in the exact same way. So, 2 lines are parallel if and only if they have the same slope. And this should make sense from how we're thinking about these parallel lines. They are the same line, just shifted up or down. Or in other words, the y-intercept just sort of got moved up or down, and the b's changed. So we're free to have any sort of y-intercept we want, but the slopes need to be exactly the same. Okay. The second type of line here is the perpendicular line. And perpendicular lines, hopefully you can read that, are a little bit more complicated. So again, we'll draw them out here and then we'll talk about them. And for two lines to be perpendicular, they need to crash into each other, but they need to crash into each other in a very specific way. We want the intersection to be a right angle. The slopes are very, very different, but in a nice way. So the slopes are related, but they're sort of exact opposites of each other. And there's two ways we can make something opposite. For example, if we had 5, we might think the opposite of 5 is negative 5, because 5 minus 5 is 0, cancels out. Or maybe we think the opposite of 5 is 1/5. So 5 minus 5 is equal to 0, sort of opposites. 5 times 1/5 is equal to 1. Again, they cancel each other out. So for a perpendicular line, which of these two ways do we want the slope to be opposite? And the answer is actually both. We want it to be as opposite as possible. So two non-vertical lines are perpendicular if and only if their slopes are negative reciprocals of each other. So the negative means we want them to sort of cancel out in the first way, and reciprocals means we cancel out in the second way. So we sort of flip it over and turn it into the denominator. So we can sort of write this down. This means the slope of the first line should be negative 1 divided by M2, where M2 is the slope of the second line. So M2 is the slope of line 2. So to get the slope, we not only flip it over, but we also make it negative. And that's all there is to it. Again, the y-intercepts can be pretty much anything we want here. And the takeaway word for this is perpendicular. Slopes are as opposite as they can be. And here, remember, two lines are parallel if the slopes are exactly the same. No change whatsoever. And that's where we'll end section 1.3, and we'll discuss some more applications in class.